time, for you right now, it flows normally. A second is a second. A minute is a minute. Constant, reliable, unchanging. But this is an illusion. In 1905, Albert Einstein discovered something. Time is breakable. It can slow down. It can stop. It can even reverse itself, theoretically. And only one thing is required for this to happen: the speed of light. In the last century, scientists have discovered 7 different ways time is broken at the speed of light. 7 different ways. The laws of physics, the reality we know, are completely shattered. And I warn you, all of these are proven, not theoretical, real. Tonight, we will explore the 7 ways, and by the end, you will understand time does not work the way you think it does. Let's begin. Part 1. The illusion of time and the first break. Time. Right now, as you're listening to this, it feels normal, steady. 1 second follows another. 1 minute becomes the next. Constant, reliable, unchanging. But here's the thing. That's an illusion. Back in 1905, a young patent clerk named Albert Einstein discovered something that would shatter everything we thought we knew about reality. He found that time isn't fixed. It's not some cosmic clock ticking the same way for everyone, everywhere. Time can bend, it can slow down, it can stretch, and in the most extreme cases, it can break entirely. And all it takes is one thing: the speed of light. Over the past century, physicists have discovered 7 distinct ways that time fractures when you approach light speed. 7 different mechanisms where the laws of physics as we experience them simply stop working, where reality itself becomes unrecognizable. And I need you to understand something crucial right now. None of this is theoretical. Every single phenomenon we're about to explore has been measured, tested, and proven. This isn't science fiction. This is science fact. In the next 90 minutes, we're going to journey through each of these 7 breaks. We'll see how time isn't what you think it is, how space itself can collapse, how cause and effect can reverse, how the universe has built-in limits that cannot be crossed. By the end, you'll never look at time the same way again. So let's begin with the first break. Time dilation. When speed slows time, the first way time breaks is called time dilation. The concept is deceptively simple. The faster you move, the slower time passes for you. But what does that actually mean? Imagine you have 2 identical atomic clocks. These are the most precise timekeeping devices humanity has ever created, accurate to within 1 second every 100 million years. You synchronize them perfectly. They're ticking at exactly the same rate. Now you leave one clock on the ground. You take the other and place it on a commercial jet. The plane takes off and circles the globe at about 600 miles per hour. 24 hours later, the plane lands. You bring the 2 clocks together and compare them. The clock that flew on the plane is behind, not by much, just 20 billionths of a second. But it's real, measurable, undeniable. The clock on the plane experienced time more slowly than the clock on the ground. Why? Because it was moving faster. This isn't a malfunction. This isn't measurement error. This is how the universe actually works. The mathematics behind the madness. Einstein gave us the equation that describes this phenomenon. It's called the Lorentz factor, and it looks like this. Time equals time prime divided by the square root of 1 minus velocity squared divided by the speed of light squared. I know, that sounds complicated. But here's what it means in practice. Let's say you're traveling at 50% of light speed. That's about 93,000 miles per second. According to Einstein's equation, for every year that passes on Earth, you would experience only about 10.5 months. Bump that up to 90% of light speed. Now, for every Earth year, you experience just over 5 months. You're aging at less than half the rate of everyone back home. At 99% of light speed, 1 Earth year equals about 7 weeks. For you, the difference is becoming extreme. At 99.9%, we're talking 16 days of your time for every Earth year. Time has slowed to a crawl for you compared to the rest of the universe. And here's where it gets truly as you approach 100%, actual light speed, time for you approaches 0. It doesn't just slow down. It essentially stops having meaning in the traditional sense. Think about that for a second. The faster you move through space, the slower you move through time. Speed and time are inversely connected in a way that seems to violate common sense. But the universe doesn't care about our common sense. GPS, proof in your pocket. Now, you might be thinking, that's interesting, but does this actually matter? Is this just some abstract physics concept that has no real-world impact? The answer is no. You rely on time dilation being true every single day. Right now, in your pocket or on your wrist, you probably have a device that depends on Einstein being right about this. Your GPS, the global positioning system, consists of dozens of satellites orbiting Earth at about 12,500 miles up. They're moving at roughly 8,600 miles per hour. That's fast, but it's nowhere near light speed. It's only about 0.001% of light speed. But here's the thing. Even at that relatively slow speed, time dilation occurs. The satellite's clocks run slower than clocks on Earth's surface because they're moving faster. We're talking microseconds per day. Tiny amounts. But there's another effect happening simultaneously. Gravity. Einstein showed that gravity also affects time. The stronger the gravitational field, the slower time moves. The satellites are much farther from Earth's center than we are, so they experience weaker gravity. This makes their clocks run faster. These two effects work in opposite directions. The speed makes satellite time slower. The weaker gravity makes satellite time faster. When you do the math, the gravity effect wins. The net result is that satellite clocks run about 38 microseconds fast every single day. 38 microseconds, that's 0.000038 seconds. Seems insignificant, right? Wrong. GPS works by measuring how long it takes radio signals to travel from satellites to your device. Radio signals move at light speed. In 38 microseconds, light travels about 7 miles. If GPS didn't correct for time dilation, your position would be off by 7 miles every single day. After 1 week, you'd have 49 miles of error. After a month, over 200 miles. GPS would be completely useless. But it's not useless. It works perfectly, because engineers program the satellites to compensate for time dilation using Einstein's equations. Every day, billions of people use technology that only functions because we understand that time is relative, the reality check. So let's recap what we've learned about the first break. Time is not universal. There's no cosmic clock that ticks the same for everyone. Your experience of time depends on how fast you're moving and how deep you are in a gravitational field. Move faster. Experience time more slowly. It's that simple and that profound. This has been proven with atomic clocks on planes. It's been verified with GPS satellites. It's been confirmed in particle accelerators. It's measured in atmospheric phenomena. It's one of the most thoroughly tested predictions in all of physics. And this is just the beginning. This is the gentlest way that time breaks. As we move forward, things are going to get much, much stranger. Because the next break shows us that time isn't just relative, it's asymmetric. And that asymmetry leads to one of the most famous paradoxes in all of physics. The setup for break 2. Here's what I want you to think about as we transition to the next section. We've established that moving fast makes time slow down for you relative to people who are stationary. Simple enough. But what if you took that to the extreme? What if you got in a spaceship and traveled at 90% of light speed for 10 years, then came back? You'd have aged less than the people who stayed home. That much is clear, but here's the puzzle. From your perspective on the spaceship, you're not moving. You're sitting still, and it's Earth that's moving away from you at 90% of light speed. So shouldn't the people on Earth age more slowly from your point of view? Both perspectives seem equally valid. So who ages less? You or them? This is called the twin paradox, and it nearly broke physics when Einstein first proposed it. Because at first glance, it seems like a genuine contradiction. If motion is relative, then both observers should see the other aging more slowly. That's impossible. So, what's the answer? How do we resolve this apparent paradox? The solution is surprising, and it reveals something fundamental about the nature of reality that most people never realize. It shows that acceleration is absolute in a way that velocity is not, that there's a fundamental asymmetry built into the fabric of space-time itself. But I'm getting ahead of myself. Let me explain this properly, because the twin paradox is our second break, and it's going to show you that time doesn't just slow down. It can genuinely create situations where two people who start the same age end up separated by decades of life experience. Where one twin can watch their sibling grow old while they remain young, not through any trick or illusion, but through the fundamental structure of the universe. And unlike some thought experiment confined to textbooks, this has been directly observed. We see it happening right now in Earth's atmosphere, dozens of miles above your head. Subatomic particles are living the twin paradox as we speak. Want to know how? Want to see the proof? Want to understand why motion isn't as relative as you might think? That's what we're diving into next. The twin paradox awaits, and trust me, the resolution is going to change how you think about motion, time, and reality itself. One more thing before we move on. Remember that feeling of time passing steadily right now? That sense of the present moment? That experience of now? That's unique to you. Every person experiences their own now, their own present. And those presents don't have to line up. Someone moving fast, relative to you, is experiencing a different present moment. Their now and your now are different slices through space-time. We all live in our own timelines. We just don't notice because we're all moving so slowly compared to light speed. But the structure is there. The framework is there. The universe is far stranger than it appears in our everyday experience. And this raises a mind-bending question. If slowing down relative to light speed slows your time, what would happen if you could go faster than it? Could you actually age backwards? That's the frontier we're crossing in our next video. Make sure you're subscribed and have notifications on, because we're not just talking theory, we're building towards the ultimate thought experiment. Time travel via light speed. You won't want to miss it. Ready for the next level? Ready to see just how strange it gets? Let's go. Part 2. The twin paradox and asymmetric time. The setup to lives diverging. Let me tell you a story about two brothers, Alex and Jordan. They're twins, born on the same day, same hour, same minute. Right now, they're both 20 years old. Identical in every measurable way. Alex has always dreamed of the stars. Jordan has always loved Earth. They're different people with different paths ahead of them. But neither of them knows just how different those paths are about to become. The year is 2050. Humanity has finally developed spacecraft capable of reaching 90% of light speed. That's about 167,000 miles per second. Alex volunteers for the first long-duration mission. Jordan stays home. The mission plan is simple. Travel to a star system 10 light-years away. Turn around, come back. From Alex's perspective on the ship, the journey will take about 10 years of subjective time. 5 years out, 5 years back. He'll return at age 30. Jordan waves goodbye from Earth. He watches the ship accelerate into the darkness. He goes back to his life. Days become weeks. Weeks become months. Months become years. He ages naturally. Gets married, has kids, builds a career. Time passes the way it always has. Then, one day, 23 years after Alex left, the ship returns. Alex steps off the spacecraft. He's 30 years old, just as expected. He looks around for his twin brother, and when Jordan approaches, Alex doesn't recognize him at first, because Jordan is 43 years old. The same person who waved goodbye 23 years ago has aged 23 years, but Alex, traveling at 90% of light speed, has only aged 10 years. They're no longer the same age. Jordan is now 13 years older than his twin brother. One departure, one journey, two completely different timelines. This is the twin paradox, and it's real. The paradox that almost broke physics. Now, here's where things get tricky. And this is where a lot of people, even some scientists initially, get confused. From Alex's perspective on the spaceship, he's not moving. That's what relativity means, right? All motion is relative to your reference frame. From Alex's viewpoint, he's sitting still in his ship, and it's Earth that's moving away from him at 90% of light speed. Then Earth moves back toward him. So by the same logic we used before, shouldn't time be moving slower on Earth from Alex's perspective? Shouldn't Jordan be the one who ages only 10 years, while Alex ages 23? Both perspectives seem equally valid. Alex sees Jordan moving. Jordan sees Alex moving. Both should see the other's clock running slow. So who's actually younger when they reunite? This apparent contradiction nearly derailed special relativity when Einstein first proposed it. Critics jumped on it. See, they said, the theory contradicts itself. It can't be right. But Einstein was right. And the resolution to this paradox reveals something profound about the universe. The resolution, acceleration, changes everything. Here's the key insight that resolves the paradox. Motion at constant velocity is relative, but acceleration is absolute. What's the difference? When you're moving at a steady speed in a straight line, there's no experiment you can do inside your vehicle to detect your motion. You could be on a perfectly smooth train, moving at 200 miles per hour, or sitting still in a station. Without looking outside, you couldn't tell the difference. That's what we mean by relative motion. But acceleration is different. When the train speeds up or slows down or turns a corner, you feel it. Objects slide around. Your coffee tilts in the cup. Your body lurches. Acceleration creates forces you can detect without any external reference. Now look at the twin paradox again through this lens. Jordan, on Earth, never accelerates. Well, he experiences Earth's rotation and orbit, but those accelerations are tiny and constant throughout the journey. For practical purposes, Jordan remains in what we call an inertial reference frame the entire time. But Alex accelerates big time. He accelerates when the ship launches. He accelerates again when the ship turns around at the halfway point. He accelerates a third time when the ship slows down to return to Earth. That's the asymmetry. Jordan's experience is fundamentally different from Alex's. Jordan stays in one reference frame. Alex switches reference frames multiple times through acceleration, and because of that acceleration, the situation is not symmetric. Alex is the one who ages less, always, every time, without exception. The paradox dissolves once you account for acceleration. Motion might be relative, but acceleration creates a real, measurable difference between the two experiences. The proof: muons raining from the sky. Okay, you might be thinking, that's a clever thought experiment. But has anyone actually observed this? Has anyone actually seen time move at different rates for objects in motion? Yes, every single day. Right above your head. Let me introduce you to muons. Muons are subatomic particles created when cosmic rays from deep space slam into molecules in the upper atmosphere, about 60 miles up. These collisions produce showers of particles, and among them are muons. Muons are unstable. They decay rapidly. On average, a muon lives for about 2 microseconds. That's 2 millionths of a second. Then it breaks apart into other particles. Now muons are fast. When they're created in the upper atmosphere, they're typically moving at 99.9% of light speed. At that velocity, in 2 microseconds, a muon can travel about 2,000 feet, less than half a mile. But here's the problem. Muons are created 60 miles up, the upper atmosphere, way above where commercial jets fly. If a muon only lives to microseconds and can only travel half a mile in that time, it should decay long before reaching the ground. And yet, we detect thousands of muons at sea level every second. They make it all the way down. They don't decay in the upper atmosphere like they should. How is that possible? Time dilation. From our reference frame on Earth, those muons are moving at 99.9% of light speed. At that velocity, time dilation is extreme. The factor is about 22. For every microsecond the muon experiences, we on Earth experience 22 microseconds. So from our perspective, the muon lives for about 44 microseconds instead of 2. That's long enough to travel about 26,000 feet, about 8 miles. Plenty of distance to make it from the upper atmosphere to the ground. But here's the fascinating part. From the muon's perspective, it still only lives to microseconds. Its internal clock hasn't changed. So how does it travel 60 miles in 2 microseconds when it should only be able to travel half a mile? The answer is length contraction, which we'll cover in detail later. But briefly, from the muon's reference frame, Earth is rushing toward it at 99.9% of light speed, and at that velocity, distances contract. The 60 miles of atmosphere gets compressed to about 2.5 miles in the muon's reference frame, so it can make the journey in its short lifetime. 2 different reference frames, 2 different explanations, but both give the same result. The muon reaches the ground. This is the twin paradox playing out in nature. The muon is Alex, aging slowly while traveling at high speed. The Earth is Jordan, aging normally, and when they meet, their clocks have diverged. Except we're not theorizing about this, we're measuring it, thousands of times per second. The evidence is overwhelming and undeniable. Real-world applications, particle accelerators, muons aren't the only place we see this effect. Every particle accelerator on Earth demonstrates the twin paradox continuously. Take the Large Hadron Collider at CERN in Switzerland. The LHC accelerates protons to 99.99999% of light speed. That's just barely slower than light, with only about 1 part in a billion separating the protons from light speed. At that velocity, time dilation is extreme. The factor is about 7,500. From the perspective of someone at rest, those protons are experiencing time 7,500 times slower than we are. And we can measure this directly because protons, when they collide, create unstable particles that decay after predictable amounts of time. Except at these extreme speeds, those decay times are stretched out by exactly the factor that Einstein's equations predict. If the particles were at rest, they'd decay in nanoseconds, but moving at near light speed, they survive for microseconds, 7,500 times longer, exactly as predicted. The LHC isn't just probing the fundamental structure of matter, it's also a time dilation laboratory. Every collision, every measurement, every data point confirms that time genuinely slows down at high velocities. The philosophical weight. Let's step back for a moment and really absorb what this means. Time is not a universal background against which events unfold. There's no cosmic clock, no absolute timeline that everyone shares. Each observer has their own personal time, their own sequence of moments, their own rate at which they age, and those timelines can diverge permanently, irreversibly. If you had an identical twin and one of you traveled at high speed while the other stayed home, you would return at different ages. You would have lived different amounts of subjective time. Your biological clocks, your memories, your experiences of duration would be fundamentally different. This isn't like crossing time zones where you just reset your watch. This is actual, physical time passing at different rates. One twin genuinely experiences fewer heartbeats, fewer breaths, fewer moments of consciousness. Now, in everyday life, these effects are tiny. You'd have to travel at speeds we can't currently achieve for years to create a noticeable age difference. The astronauts who've spent the most time in orbit have aged perhaps a few milliseconds less than they would have on Earth. Negligible. But the principle is proven. The mechanism is real. And it raises profound questions. If time can pass at different rates for different people, what does that mean for concepts like simultaneous events? If I observe two things happening at the same time, but you're moving relative to me, you might see them happening at different times. So which of us is right? The answer is both, and neither. Simultaneity is relative. There's no absolute now that extends across the universe. Your now and my now are different if we're in relative motion. Think about that. Right now, as you're hearing these words, someone in a spaceship moving past Earth at high speed would have a completely different definition of right now than you do. Events you perceive as happening simultaneously would not be simultaneous from their perspective. The universe doesn't have a universal present moment. It has countless presents, all equally valid, all depending on the observer's motion. The second break. Summary. So here's what we've learned about the second break. Time dilation isn't just about time slowing down. It's about time becoming personal. Your timeline is yours alone. And if you change velocity, if you accelerate and decelerate, your timeline can diverge from someone else's in a permanent, measurable way. The twin paradox isn't a paradox at all once you understand that acceleration breaks the symmetry. The twin who accelerates is the twin who ages less, always, every single time, and we see this in nature constantly. muons living longer than they should, particles in accelerators surviving when they should have decayed, GPS satellites requiring constant corrections to stay synchronized. Time is flexible. Time is personal. Time is breakable. But we're only 2 breaks in. We've seen how time slows at high speeds and how that slowdown is asymmetric. But we haven't yet addressed one of the biggest questions. Why? Why does the universe work this way? Why can't we just accelerate to light speed? What's stopping us? The third break answers that question. And the answer is both simple and terrifying. If you could exceed light speed, you wouldn't just be traveling fast. You'd be breaking causality itself. You'd be allowing effects to come before causes. You'd be opening the door to paradoxes so severe that reality itself would become inconsistent. The universe doesn't allow that. It can't allow that, and so it built in a speed limit, an absolute boundary that nothing with mass can cross. The speed of light isn't arbitrary, it's the speed at which cause and effect remain intact. Go faster, and you don't just travel quickly. You break the logical structure of reality. Want to see how? Want to understand why exceeding light speed would let you send messages into your own past? Want to know why the grandfather paradox isn't just science fiction, but a real constraint on what physics allows? That's next. The third break, where we discover that the speed of light is less about speed and more about preserving the sanity of the universe itself. Because without it, time wouldn't just slow down or speed up, it would fold back on itself. And that way lies madness. Part 3. Causality, breaking, and the light speed barrier. The foundation of reality. Cause and effect. Before we dive into the third break, we need to talk about something so fundamental that we rarely think about it. Something so basic that it seems almost silly to mention. Cause and effect. Every single thing that happens in the universe follows a pattern. First, something causes an event. Then the effect happens. Always in that order. Cause first, effect second. Never the other way around. You drop a glass, it falls, it shatters. The dropping causes the falling causes the shattering. You can trace the chain of causality backward from the broken pieces on the floor all the way to your hand letting go. You flip a light switch. Electricity flows. The bulb illuminates. Each step follows logically from the previous one. The sequence is sacred, unbreakable, absolute, or so we think, because here's what Einstein discovered and what most people never realize. The speed of light isn't just a speed limit, it's the speed of causality itself. It's the maximum rate at which cause can influence effect across space. And if you could somehow exceed that speed, you wouldn't just be moving really fast. You'd be violating the fundamental logical structure of the universe. You'd be allowing effects to precede their causes. You'd be breaking time itself. The thought experiment, a bullet faster than light. Let me show you what I mean with a thought experiment. And I want you to really follow along here, because this is where things get genuinely weird. Imagine you've invented a gun. Not a normal gun, but one that fires bullets at 150% of light speed. Completely impossible in reality, but bear with me. This is about understanding why it's impossible. You set up a target 300,000 miles away. That's roughly the distance light travels in 1 second. You aim the gun, you pull the trigger at exactly 12 noon. The bullet leaves the gun at 1.5 times light speed. It reaches the target in 0.67 seconds. So at 12 noon and 0.67 seconds, the target explodes. Simple enough, right? Cause at noon. Effect at noon and 0.67 seconds. The normal sequence holds. But now let's add another observer. Someone in a spacecraft moving past you at, say, 80% of light speed at the moment you fire. From your perspective, events are clear. You fire at noon. Target explodes 0.67 seconds later. Cause, then effect. But from the moving observer's perspective, something impossible happens due to the relativity of simultaneity, which is a consequence of special relativity. Events that appear sequential to you can appear in a different order to someone moving relative to you, and when the signal connecting those events moves faster than light, the reversal becomes possible. From the moving observer's perspective, the target explodes before you pull the trigger. The effect happens before the cause, the mathematics of madness. Now, I'm not going to write out the full mathematical derivation here because we're focusing on understanding, not equations, but the core insight comes from something called the Lorentz transformation, which describes how space and time coordinates change between different reference frames. When you apply this transformation to events connected by a faster-than-light signal, the time ordering can flip. Not for slow-moving observers, not for observers moving in certain directions, but for observers moving fast enough in the right direction relative to the signal. This isn't a quirk of the math. This is a fundamental consequence of how space-time works. Events that one observer sees as separated in time can appear simultaneous to another observer. And if the signal connecting them is fast enough, a third observer can see them reversed. Think about what that means. From one perspective, you shoot first and hit the target second. From another perspective, the target explodes first and then you shoot. Both perspectives are equally valid according to the laws of physics, but that's logically inconsistent. How can the target explode before you fire? What caused it to explode if your bullet hasn't been fired yet? This is the problem. Faster than light travel doesn't just let you move quickly. It breaks causality. It allows effect without cause. It creates logical paradoxes that cannot be resolved. Time travel and the grandfather paradox. And here's where it gets even more mind-bending. If you can send a signal faster than light, you can effectively send a message into the past. Here's how. You send a faster-than-light signal to a spaceship moving away from you. From your perspective, the signal arrives in the ship's future. But from the ship's perspective, due to relativity of simultaneity, the signal might arrive in its past. The ship then sends a faster-than-light signal back to you. Again, due to the motion and the relativity of simultaneity, this return signal could arrive at Earth before the original signal was sent. You've created a closed time-like curve, a path through space-time that loops back on itself. You've received a message from your own future, and once you can do that, you can do anything. You can send yourself lottery numbers. You can warn yourself about disasters. You can change past events. But most famously, you run into the grandfather paradox. You use your faster-than-light communication to send instructions to your past self. Those instructions lead to a chain of events where your grandfather dies before your parents are born. You cease to exist. But if you never existed, who sent the message? Paradox. The universe doesn't do paradoxes. Logic doesn't allow contradictions. Reality must remain self-consistent. So the universe has a rule, a hard boundary, a line that cannot be crossed. That boundary is the speed of light. Not because light is special, but because causality must be preserved. Why light speed exactly? You might be wondering, why this speed specifically? Why 186,000 miles per second? Why not faster or slower? The answer is that light speed isn't really about light. It's about the structure of space-time itself. It's the conversion factor between space and time. It's the speed at which massless particles must travel. It's the cosmic speed limit built into the fabric of reality. Light happens to travel at this speed because photons have no mass. But gravitational waves also travel at this speed. So would any hypothetical massless particle. The speed is fundamental. Light just makes it visible to us. In a sense, calling it the speed of light is a historical accident. We discovered it by studying light. But really, it's the speed of causality. The speed of information. The maximum rate at which influence can propagate through space. And it has to be finite. If causality could propagate instantly, if action at a distance were possible, then there would be no constraint on the ordering of events. Different observers could see any sequence they wanted. Reality would lose coherence. So the universe enforces a speed limit. Cause can only affect things within its future light cone. Events outside that cone are causally disconnected. The structure holds. Paradoxes are prevented. Real-world evidence. Cosmic rays. Now, you might think this is all theoretical thought experiments about impossible guns and hypothetical scenarios. But we actually see evidence of this speed limit constantly. Cosmic rays are high-energy particles from space that slam into Earth's atmosphere. Some of these particles have truly enormous energies. The most powerful cosmic ray ever detected, called the Oh My God particle, had an energy equivalent to a baseball traveling at 60 miles per hour, concentrated in a single proton. That's an absurd amount of energy for something so small, and that energy translates into speed. The Oh My God particle was traveling at 99.999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 51% of light speed. Let me put that in perspective. If you were racing light across the galaxy, and light finished in 100,000 years, this particle would finish about 0.1 seconds later. It's absurdly close to light speed, but it's not at light speed. It's not even close to exceeding light speed. Despite having ridiculous amounts of energy, it's still bound by the limit. Why? Because as you add energy to a particle with mass, most of that energy goes into increasing the particle's relativistic mass, rather than its speed. You can pump infinite energy into it, and it will never quite reach light speed. It will asymptotically approach it, getting closer and closer, but never arriving. The universe refuses to let massive particles reach the barrier. The math breaks down. The energy required becomes infinite. And infinity isn't a number you can achieve with finite resources. The third break. Summary. So here's what we've learned about the third break. The speed of light isn't just a speed limit. It's a causality limit. Exceed it, and cause and effect can reverse. Effects can precede causes. Messages can arrive before they're sent. The logical structure of reality unravels. The universe prevents this by making the speed of light unattainable for anything with mass. You can get arbitrarily close, but you can never reach it, let alone exceed it. This isn't a technological limitation. This isn't about our engineering not being good enough yet. This is a fundamental constraint on reality itself. The universe says no, and it enforces that no through the mathematics of space-time. Every particle accelerator confirms this. Every cosmic ray demonstrates it. Every attempt to push particles faster runs into the same wall. The energy requirements grow exponentially. The returns diminish. The limit holds firm. But why? What's the mechanism? How does the universe enforce this speed limit? That brings us to the fourth break. And this one's about energy. Specifically, about what happens to mass and energy as you approach light speed. Because here's the thing, when you try to accelerate something, you're adding energy to it. And Einstein showed that mass and energy are equivalent. They're two forms of the same thing. So when you add energy to an object, you're not just making it faster, you're making it heavier. The faster you go, the more massive you become. And the more massive you are, the harder it is to accelerate you further. It's a vicious cycle, a feedback loop, an infinite wall that you slam into as you approach the speed of causality. Want to see the numbers? Want to understand exactly how much energy it would take to accelerate even a small mass to light speed? Want to know why particle accelerators can get protons to 99.9999% but not 100%? That's next. The fourth break, where we confront the infinite energy barrier, where we see that the universe doesn't just discourage faster than light travel, it makes it mathematically impossible. Because at light speed, mass becomes infinite, and infinite mass requires infinite energy. And infinity is not a number you can work with. The universe has walls, hard walls, absolute boundaries. And we're about to crash into the biggest one of all. Part 4. The infinite energy wall and collapsing space. E equals mc squared, the most famous equation. Let's talk about the most famous equation in physics. 3 symbols that changed everything we thought we knew about the universe. E equals mc squared. Energy equals mass times the speed of light squared. Most people have heard this equation. Fewer people understand what it actually means. And almost nobody grasps its full implications for why we can never reach light speed. Here's the core insight. Mass and energy aren't different things. They're the same thing in different forms. Mass is just extremely concentrated energy. Energy is just dispersed mass. They're interchangeable. When you add energy to something, you're not just making it move faster or get hotter. You're literally increasing its mass. The object becomes heavier, not metaphorically, actually, physically heavier. In everyday life, we don't notice this because the speed of light squared is such an enormous number. You'd have to add tremendous amounts of energy to create even a tiny increase in mass. But at extreme speeds, approaching light speed itself, this effect becomes dominant. And it creates an insurmountable barrier, the mass increase. Running the numbers. Let's start with something familiar. You, a human being. Let's say you weigh 150 pounds. That's about 68 kilograms. That's your rest mass. Your mass when you're sitting still. Now let's imagine accelerating you to higher and higher speeds and watching what happens to your mass. At 10% of light speed, about 18,600 miles per second, your mass increases to about 151 pounds. Only 1 extra pound, barely noticeable. At 50% of light speed, you're up to about 173 pounds, 23 pounds heavier. That's significant, but not crazy. At 90% of light speed, things start getting wild. Your mass is now 330 pounds, more than double your rest mass. You've gained 180 pounds just from moving fast. At 99%, you're at 1,060 pounds, over 7 times heavier than when you started. You're carrying an extra 900 pounds of mass, created entirely from kinetic energy. At 99.9%, you're at 3,370 pounds, 22 times your original mass. You weigh as much as a small car. See the pattern? As you get closer to light speed, your mass doesn't just increase linearly, it explodes exponentially. The closer you get to 100%, the faster the mass grows. And at exactly light speed, your mass becomes infinite. The energy cost, quantifying the impossible. Now let's flip this around. Instead of watching mass increase, let's calculate how much energy it takes to accelerate you to these speeds. Getting you to 10% of light speed requires about 3.4 times 10 to the 17th power joules. That's a huge number, but let me make it concrete. That's roughly the energy output of a large power plant running for several days. 50% of light speed. Now we're at 2.5 times 10 to the 18th power joules. That's approaching the total energy consumption of all human civilization for an entire day. 90% of light speed requires about 6 times 10 to the 18th power joules. That's several days of global energy consumption. Every power plant, every car, every light bulb on Earth running continuously for days, all to accelerate one person at 99%. We're at 2.3 times 10 to the 19 power joules. That's weeks of global energy output. The entire planet working around the clock just to move you. 99.9%. 1.7 times 10 to the 20 power joules. Months of global energy. Every joule of electricity generated worldwide for months, focused entirely on accelerating one human being. And the closer you get to 100%, the worse it gets. At 99.99%, you'd need years of global energy output. At 99.999%, decades. At exactly 100%, infinite energy. Not a lot of energy. Not more than we currently have. Infinite. As in, you could harness every star in the galaxy, every black hole, every scrap of energy in the observable universe, and it still wouldn't be enough, because infinity isn't a really big number. It's not a number at all. CERN, watching the wall. This isn't speculation. We see this barrier in action every single day at particle accelerators around the world. The Large Hadron Collider at CERN is the most powerful particle accelerator ever built. It's a ring 17 miles in circumference, buried under the border between France and Switzerland. It uses superconducting magnets, cooled to near absolute zero, to accelerate protons to incredible speeds. How fast can it go? Well, they can get protons up to 99.999991% of light speed. Let me write that out so you can see it. 99.999991%. They're getting within 1 part in a billion of light speed. At that velocity, the protons are experiencing time dilation by a factor of about 7,500. From our perspective, they're living 7,500 times longer than they normally would, and their mass has increased by the same factor. A proton normally weighs about 1.67 times 10 to the negative 27 kilograms. At full LHC speed, it weighs about 7,500 times more, still incredibly tiny by human standards, but 7,500 times heavier than it should be. To achieve this, CERN pumps an enormous amount of energy into these protons. Each proton carries about 7 trillion electron volts of kinetic energy. The full beam contains about 360 trillion protons, carrying a combined energy of about 362 million joules. That's roughly equivalent to an aircraft carrier moving at 30 miles per hour. All concentrated in particles smaller than atoms. But here's the key point. They can't get to 100%. They can't even get meaningfully closer than they already are. To get from 99.999991% to 99.9999999%, they'd need to double the energy of the entire accelerator. And to get from there to 100% would require infinite energy. The wall is real. The universe enforces it absolutely. Length contraction, space collapses. But mass and energy aren't the only things that go haywire at light speed. Space itself starts behaving strangely. This is the fifth break, and it's called length contraction. Here's what happens. As you accelerate toward light speed, distances in the direction you're traveling appear to shrink. Not from the perspective of someone watching you, but from your own perspective. If you're heading toward a star 1 million miles away, and you're moving at 50% of light speed, that distance shrinks to about 866,000 miles from your reference frame. You're experiencing space itself as compressed. At 90% of light speed, the million miles contracts to about 436,000 miles. At 99%, it's down to 141,000 miles. At 99.9%, only about 45,000 miles. The faster you go, the more space contracts ahead of you. Distances that seem vast to stationary observers appear manageable to you because space itself is squeezing down. At 99.99% of light speed, that million-mile journey contracts to about 14,000 miles. At 99.999%, it's just 4,500 miles, and at exactly light speed, the distance contracts to zero. The entire universe ahead of you, in the direction of your motion, compresses into a single point. Infinite distance becomes zero distance. But here's where physics gets wild, and where our next journey begins. We've seen what happens at the cosmic speed limit, but it forces us to ask the ultimate question: what about beyond it? If you could somehow cross that forbidden line, would the mathematics of relativity flip on its head? Could a journey of zero distance become negative? And could that mean you arrive before you leave? Could you, in fact, age backwards? That's exactly what we're tackling next time. We're moving from the twin paradox to the realm of pure speculation, where time travel isn't just a story, but a mathematical possibility. The answer will change how you see cause and effect forever. If you don't want to miss that, make sure you're subscribed and notifications are on. This is one trip through space-time you won't want to watch late. Until then, keep questioning the visual experience. Reality distorts. Let me paint you a picture of what you'd actually see if you were somehow traveling at 99.9% of light speed. Looking forward, you'd see something bizarre. All the stars ahead of you would appear compressed into a tight circle, maybe just a couple degrees across. The entire forward view of the universe, billions of light years of space, squeezed into a spot smaller than your fist, held at arm's length. The stars would also be shifted because you're rushing toward them so fast. Their light waves compress, shifting toward higher frequencies. Blue light becomes ultraviolet. Visible light becomes blue. The universe ahead glows with an eerie, compressed luminescence. Looking to the sides, you'd see almost nothing. Darkness. The relativistic beaming effect means light from the side barely reaches you. It's all concentrated ahead and behind. Looking backward, you'd see another tight circle of stars, everything behind you, including Earth, compressed into a small disk. These stars would be redshifted, their light stretched to longer wavelengths because you're moving away from them so fast. You'd feel like you're flying through a tunnel. The universe ahead and behind compressed into bright circles, the sides dark and empty. Space itself warped beyond recognition. And if you somehow reached exactly light speed, that forward circle would contract to a single point. Every star, every galaxy, every structure in the universe ahead of you would merge into one infinitesimally small location. Space would cease to have extension in the direction of your travel. the fifth break, space itself collapses to zero. Gravity intensifies. You become dense. We've talked about how your mass increases as you approach light speed, but mass doesn't exist in isolation. Mass creates gravity. And as your mass increases, so does your gravitational field. At 99.9% of light speed, you're 22 times more massive than normal. That means your gravitational field is 22 times stronger. Objects near you experience 22 times the gravitational pull they normally would. At 99.99%, you're 223 times more massive. Your gravity is 223 times stronger. You're pulling on nearby objects like a small asteroid. At 99.999%, your mass has increased by a factor of over 700. You're creating gravitational effects comparable to a small moon. Space near you is noticeably warped by your presence. Keep going. At 99.9999%, your mass factor is over 7,000. You're bending space like a planet. Light passing near you would visibly curve, and at 100%, infinite mass means infinite gravity. You would become what's called a singularity, a point of infinite density, a black hole. This is the sixth break. At light speed, you don't just gain mass, you become a gravitational impossibility. The universe can't allow objects with mass to reach light speed because they would collapse into singularities. Reality would break down. The barrier holds. Let's take stock of what we've learned in this section. We've discovered multiple reasons why the universe prevents anything with mass from reaching light speed. First, the energy wall. As you approach light speed, your mass increases, and the energy required to accelerate you further grows without bound. At light speed, the energy requirement becomes infinite. Second, the space collapse. Distances in your direction of travel contract toward zero. At light speed, the entire universe ahead of you becomes dimensionless. Third, the gravity explosion. Your increasing mass creates an increasingly powerful gravitational field. At light speed, that field becomes infinitely strong, creating a singularity. These aren't three separate problems. They're three manifestations of the same underlying reality. The structure of space-time itself forbids massive objects from reaching the speed of causality. The math breaks down. The equations produce infinities. The physics becomes undefined. The universe says no in the strongest possible terms. But there's one more break we haven't discussed yet. One more way that time fractures at light speed, and this one might be the strangest of all. The final break preview. Because here's something to think about. We've been talking about what happens as you approach light speed, but there's one thing in the universe that actually travels at light speed, not close to it, exactly at it. Light itself, photons, the particles that make up electromagnetic radiation, and photons experience reality in a way that's fundamentally different from anything with mass. They don't just experience time slowly, they don't experience time at all. From a photon's perspective, if we can even use that phrase, there is no time. A photon is created, travels any distance, and is absorbed all in the same instant. Zero elapsed time. Not a short time. Not a long time. No time. The journey from a star 8 light years away, from the photon's perspective, instantaneous. The moment of emission and the moment of absorption are the same moment. There's no duration, no experience, no existence in the temporal sense. This is the seventh and final break. At light speed, time doesn't slow down, it doesn't stop, it becomes undefined. The concept itself loses meaning. How can something exist with no time? How can a photon travel across the universe if, from its perspective, no time passes? What does it mean for time to be undefined rather than zero? That's what we're exploring next. The final break, where we confront the ultimate strangeness of light speed, where time itself ceases to exist as a meaningful concept. Are you ready to see just how deep this rabbit hole goes? Part 5. The timeless photon and 7 breaks united. The photon's journey, 8 minutes of nothing. Right now, as you're listening to this, photons from the sun are striking your skin. They've traveled 93 million miles through the vacuum of space. From our perspective here on Earth, that journey took about 8 minutes and 20 seconds. Light leaves the sun's surface, crosses the solar system, and arrives at Earth 8 minutes and 20 seconds later. But here's the mind-bending part. From the photon's perspective, no time passes at all. 0 seconds. Not a tiny fraction of a second. Literally 0. The moment of departure and the moment of arrival are the same moment for the photon. It's created in the sun's outer layers and absorbed by your retina in what is, from its reference frame, a single instantaneous event. How is this possible? How can something travel 93 million miles in 0 time? What does it even mean for time to be 0? This is the 7th and final break, and it's the most profound one of all. Time dilation at the limit. Remember the time dilation formula we discussed earlier. Time experienced equals time observed divided by the square root of 1 minus velocity squared divided by light speed squared. Let's see what happens when we plug in exactly light speed for the velocity. The velocity divided by light speed equals 1. 1 squared equals 1. 1 minus 1 equals 0. The square root of 0 is 0. So we get time experienced equals time observed divided by 0. Division by 0. In mathematics, that's undefined. It's not infinity. It's not a really big number. It's literally undefined. The operation has no meaning. The formula breaks down completely. This isn't a bug in the equations. This is the universe telling us something fundamental. At light speed, the concept of time passing doesn't just become extreme, it becomes meaningless. Time doesn't exist for a photon in any sense we can comprehend. Think about what that implies. Every photon that has ever existed, from the Big Bang to now, has experienced exactly the same amount of proper time. 0. A photon created in the first moments after the universe began and a photon created 1 second ago have both experienced identical durations from their perspective. None. The entire history of the universe, all 14 billion years of cosmic evolution, is instantaneous from light's point of view. Living without time, the photon experience. Let's try to imagine what this means. Even though it's truly impossible for beings like us who exist in time, a photon is born in a star. Maybe it's created by nuclear fusion in the core of the sun, or by an electron dropping to a lower energy level in a distant galaxy, or by some violent event in a supernova billions of light years away. From our perspective, that photon then travels. It moves through space at 186,000 miles per second. It might journey for seconds, years, or billions of years. It might pass through clouds of gas, skirt around black holes, traverse the vast emptiness between galaxies. Eventually, it reaches its destination. Maybe it hits your eye. Maybe it strikes a solar panel. Maybe it's absorbed by a molecule in Earth's atmosphere. The journey ends. From the photon's perspective, there was no journey. The moment of creation and the moment of absorption are the same moment. The beginning and end are simultaneous. The entire trip, regardless of distance, occupies zero duration. The photon doesn't experience travel. It doesn't experience existence. It doesn't experience anything because experience requires time, and time doesn't exist at light speed. This is what the seventh break tells us. At light speed, time isn't just slow. It isn't just stopped. It's absent. The dimension of time ceases to be a dimension at all. Why mass cannot reach this state? Now you might be wondering why photons can exist in this timeless state, but massive objects cannot. Why does the universe allow photons to travel at light speed but forbids electrons or protons or human beings from doing the same? The answer comes back to what we learned in the previous section. Objects with mass have rest energy. They have an inherent energy content even when they're not moving. That's what mass is, fundamentally, condensed energy that persists even in a rest frame. Photons have no mass, zero rest energy. They cannot exist at rest. They must always travel at light speed. It's not that they choose to move at that speed, it's that they cannot exist any other way. A photon at rest is a contradiction in terms. But anything with mass has a rest frame, a reference frame where it's stationary. And because it can be stationary, because it has rest energy, it can never reach light speed. To do so would require infinite energy, as we saw before. The mass would become infinite. The object would collapse into a singularity. The universe makes a hard distinction. Massless particles must travel at light speed and experience no time. Massive particles must travel slower than light speed and experience time normally. There's no in-between, no gradual transition, just a sharp boundary that cannot be crossed. The seven breaks unified. Let's step back now and look at everything we've discovered. 7 different ways that time and space break down at light speed. 7 manifestations of the same underlying truth. The speed of light is not just a speed limit. It's a fundamental boundary in the structure of reality itself. Break 1. Time dilation. As you approach light speed, time slows down for you relative to stationary observers. Your clock ticks slower, your heartbeat slows, your experience of duration contracts. At light speed, time dilation becomes infinite. Break 2. The twin paradox. Time dilation is asymmetric. The person who accelerates ages less than the person who remains stationary. This isn't a symmetric effect. It's a genuine difference created by acceleration. We see it in particle decay rates. We measure it with atomic clocks. It's as real as gravity. Break 3. Causality violation. If you could exceed light speed, cause and effect would become unstable. Effects could precede causes. Messages could arrive before being sent. The logical structure of reality would collapse. The universe prevents this by making light speed unattainable. Break 4. The infinite energy wall. As you approach light speed, your mass increases. The energy required to accelerate you further grows without bound. At light speed, both mass and energy become infinite, an insurmountable barrier built into the mathematics of space-time. Break 5. Length contraction. Space itself compresses in the direction of motion. Distances shrink as you accelerate. At light speed, all distance ahead of you collapses to zero. The universe becomes dimensionless in your direction of travel. Break 6. Gravitational singularity. Your increasing mass creates an increasingly powerful gravitational field. At light speed, infinite mass means infinite gravity. You become a black hole. a singularity, a breakdown of space-time itself. Break 7. The absence of time. At light speed, time doesn't slow or stop. It becomes undefined. The concept loses meaning. Photons exist in an eternal now, experiencing no duration, no change, no temporal progression. 7 breaks. 7 ways the universe says no. 7 reasons why light speed is the ultimate limit. What this means for reality. So what should we take away from all of this? What does it mean for our understanding of the universe? First, time is not what we think it is. It's not a universal background against which events unfold. It's not a cosmic clock ticking the same for everyone. Time is personal, relative, flexible, and under extreme conditions, completely breakable. Every person has their own timeline. Your now is not the same as my now if we're in relative motion. Your rate of aging is not the same as mine if we're at different speeds or in different gravitational fields. We each experience our own unique path through space-time. Second, the universe has absolute limits, not technological limits, not limits based on our current engineering capabilities. Absolute mathematical boundaries that cannot be exceeded, no matter how advanced civilization becomes. You cannot travel faster than light. You cannot send information faster than light. You cannot violate causality. The structure of space-time itself prevents it. Any theory that predicts faster than light travel is either wrong or requires exotic physics we haven't discovered yet. Third, everything we've discussed is happening right now, all around us. It's not science fiction. It's not distant speculation about far future technology. GPS satellites are experiencing time dilation at this very moment. Muons in the upper atmosphere are living the twin paradox. Cosmic rays are slamming into the atmosphere at 99.99% of light speed. Their masses increased thousands of times. Photons from distant stars are arriving in our telescopes, having experienced zero time despite traveling for billions of years. The breaks are real. The effects are measurable. The universe operates this way whether we understand it or not. The human perspective. What about us? Now, you might be feeling a bit overwhelmed by all of this. The universe suddenly seems strange, alien, counterintuitive. The comfortable assumptions we make about time and space have been shattered. But here's the thing. For us, for human beings living normal human lives on Earth's surface, none of this matters in practical terms. We move so slowly compared to light speed that relativistic effects are negligible. The fastest humans have ever traveled is about 25,000 miles per hour. That's the speed of the Apollo spacecraft returning from the moon. Sounds fast, right? It's about 0.0037% of light speed, absurdly slow on the cosmic scale. At that speed, time dilation is about 6 parts per billion. If you spent a year traveling at 25,000 miles per hour, you'd age about 0.2 seconds less than someone on Earth, completely unnoticeable. So, in our everyday lives, time appears universal. Clocks tick at the same rate. Causality is strict and linear. Space doesn't contract. Mass doesn't increase. The breaks are there, but they're hidden beneath layers of normalcy because we're so slow. But the structure exists. The potential is there. And if we ever develop the technology to travel at significant fractions of light speed, we'll have to confront these effects directly. Future possibilities, can we use this? This raises an interesting question. Can we exploit time dilation for practical purposes? Could we use it for interstellar travel or for reaching the distant future? The answer is yes, in theory. If you could build a spacecraft capable of 99.9% of light speed, you could travel enormous distances while experiencing relatively little personal time. From your perspective on such a ship, you could cross the galaxy in what feels like a few years. The trip might take 100,000 years from Earth's perspective, but for you, it would be much shorter. Time dilation works in your favor, of course. You'd return to an Earth where 100,000 years have passed. Everyone you knew would be long dead. Civilization would be unrecognizable. You'd be arriving in the deep future, having skipped over millennia of history. This is a one-way trip into the future. You can move forward in time rapidly by traveling fast, but you can never come back. You can never return to your original time. The asymmetry of the twin paradox ensures that could we ever actually build such a spacecraft? That's an engineering question, not a physics question. Physics allows it. The laws of relativity permit travel at 99.9% of light speed, or even closer, but the energy requirements are staggering. The technological challenges are immense. We're nowhere close to achieving it with current technology, but it's not forbidden. It's possible in principle, and that's what matters for physics. The universe allows it, even if we don't yet know how to do it. The ultimate truth, light speed rules everything. As we reach the end of this journey, let's return to where we started. Time is not what you think it is. It's flexible. It's personal. It's relative to your motion and your position in gravitational fields. It can slow down, speed up, and under extreme conditions, cease to have meaning entirely. The speed of light isn't really about light. It's about the structure of space-time. It's the conversion factor between space and time. It's the speed of causality. It's the maximum rate at which information can propagate through the universe, and it creates a hard boundary, a limit that cannot be exceeded. Not because we lack the technology, but because the universe itself forbids it through 7 different mechanisms, each one sufficient on its own to prevent faster-than-light travel. We've seen how time dilates, how the twin paradox creates asymmetric aging, how causality would break down, how energy requirements become infinite, how space contracts to zero, how mass explodes to create singularities, and how time itself becomes undefined. 7 breaks, 7 facets of the same fundamental truth. Light speed is the speed limit of reality. Living in a relativistic universe. So what does this mean for you, listening to this right now? How should this knowledge change the way you think about the world? First, be amazed. The universe is far stranger and more beautiful than everyday experience suggests. The fact that time is relative, that simultaneity depends on motion, that the speed of light connects space and time in such a profound way. These are extraordinary truths about reality. Second, be humble. Humans evolved to understand motion at walking speeds, distances of a few miles, timescales of decades. We did not evolve to intuitively grasp relativistic physics. The fact that the universe behaves counterintuitively at extreme speeds isn't a failure of the universe. It's a limitation of our intuition. Third, trust the math and the evidence. Every prediction of special relativity has been confirmed experimentally. Time dilation is real. Length contraction is real. Mass increase is real. The speed of light limit is real. Thousands of experiments over more than a century have verified these effects. And finally, never stop asking questions. Physics has revealed extraordinary truths about time and space, but there's still so much we don't know. How does quantum mechanics fit with relativity? What is dark energy? Can space-time itself be warped in ways that allow effective, faster-than-light travel without violating causality. The universe holds deeper mysteries still, and every answer raises new questions. The final word: time breaks at light speed, 7 different ways, 7 manifestations of a single profound truth. The universe has rules, and those rules are absolute. We've journeyed through the mathematics, the thought experiments, the real-world evidence. We've seen how GPS depends on relativity, how muons demonstrate the twin paradox, how particle accelerators slam into the infinite energy wall, how photons experience no time at all. This isn't abstract philosophy. This is physical reality, tested, verified, confirmed in countless ways. The speed of light stands as the ultimate boundary, not a challenge to overcome, but a fundamental feature of how reality is constructed. Cause must precede effect. Time must remain consistent. The universe must make sense. And to ensure all that, light speed cannot be exceeded. So the next time you see light from the sun, remember, those photons traveled 93 million miles in 8 minutes from your perspective. But from their perspective, no time passed at all. They were born and died in the same instant, experiencing the entire journey as a single timeless moment. And if you could somehow travel at light speed yourself, you too would exist outside of time, not as a person anymore, but as something else entirely. A being for whom past, present, and future collapsed into an eternal now. But you can't, because you have mass, and the universe has rules, and those rules keep reality stable, logical, and consistent. Time breaks at light speed, but only in ways that preserve the sanity of the universe itself. Yet, the human mind can't help but push at the boundaries of those rules. We've seen what happens at the limit, so we're forced to ask the ultimate what if. What if you didn't just reach that limit, but slipped past it? Could the equations that break time at light speed reverse it if you go faster? Could you, in theory, age backwards? That is the thrilling cliffhanger we step into tomorrow. Thank you for taking this journey with me today. If you want to follow the next one into the realm of the seemingly impossible, make sure you're subscribed. The question awaits: can you age backwards if you travel faster than light? Until then, keep looking up, keep asking questions, keep marveling at how strange and beautiful reality truly is.